Everyone, welcome to the class of differential equations and the matrices. And this time we are moving to section 3.6, basis and the dimension. And we got a few other things to clarify before we can reach to basis and the dimension. First, the concept, it is linear combination. And let's say V is the vector space. Remember vector space? A vector space basically it is set with two operations and it must be closed on the scalar multiplication and the vector addition. So V is a vector space. A linear combination of those vectors V1, V2 all the way to Vn, it is the vectors generated in such a way, okay, the constant multiple of each vector and then add to the others, okay, the sum of the constant multiples of those vectors adding together, that's a linear combination. Okay, the collection of the linear combination, it is called as the span of those vectors, the span of those vectors. And the one thing you may want to know, the span actually it is closed. And we are working under the assumption of a vector space. Indeed, the span it is a subspace of the big vector space here. Maybe let's take a look what is span over here. Okay, so I do have first example. Actually, it is the example from the textbook. We are having two vectors, u and v, and let's take a look how the span would look like. The span of u and v, it is a linear combination of u and v. Certainly, a and b are some scalars or real numbers. Okay, so I just add AU and BV together. And with all the components, it turns out to be 3A. First component, second component, 2A plus 2B, third one as 2B. And indeed, what I'm saying here is all the factors in the span must be in this fashion. You could choose A and B as any form, and then the vector must be in this fashion. Vector must be in this fashion, generated with those components. And also to see it clearly what this span really would look like. So this is what I did. I say any vector in the span, well, it's a linear combination of three-dimensional vectors, right? So at least it still will have to be a three-dimensional vector. And then I compared this three-dimensional vector with the components. So simply says x equals 3a, y equals 2a plus 2b, and z equals 2b. And then if we make a manipulation, solve A from the first equation here, solve B from the third equation, then put everything back to the equation in the middle. So this gives us some idea, well, I would say maybe kind of better idea how the span looks like. It is in this fashion. It is in this fashion. Y equals 2/3 times x plus z. And indeed, still if it's not that clear, we could put x, y, z all together. You see the linear equation, right? So this is the equation of plane passing through the origin, So indeed, now somewhat geometrically, speaking of the graph, we can say the span of those two three-dimensional vectors indeed turns out to be a plane. But anyway, it should be clear. The plane, it is really not the xy plane usually we talk about, the R2. Okay, it is just a plane in the three-dimensional space. It is a plane in the three-dimensional space. That is the span of a set. Span, it is a collection of all linear combinations. And somewhat we figured out now we are having two three-dimensional vectors, and indeed they do span a two-dimensional, actually they do span a plane in the three-dimensional space. Okay, that is span. And then let's take a look basically, I'm still using those two vectors, u and v. Okay, u and v are the same in example 2. Then I'm adding a vector w here. I'm adding a vector w, and it's taking as negative 3, 2, and 4. And one thing before we go further, it's just very well manipulated example, okay, no particular reason. The w here, indeed, if you take a look, w, indeed, itself can be written as a linear combination of u and v. I believe this should be correct. Negative u plus 2v. Negative u plus 2v, it's equal to generate w. So w itself, it is a linear combination of u and v. In the linear combination of u, v, w, whenever you have w, it always can be replaced with u and v. So this is what I observe in this part A, example 2, part A. Adding w to this given set, u and v, it's not going to change anything, because the linear combination of u, v, w, it is just the same as the linear combination of u and v. So I said the span of u, v, w, it is really the same as span of u and v. I hope it's clear. Example 2, part A. The span of two vectors. Then we realize adding a vector in the group, it may not change the span at all, like in this case. And then how about let's give a try to see if we can add another vector, what would happen. So the other vector we are considering to add here, it is in this fashion, vector x. And now it is a good point to answer maybe how do we know this w can be written as a linear combination. Well, basically, we really don't know. So this time, we just assume x is also linear combination of u and v, which means we want to find out the constants, if all possible, c1 and c2. So this time, I give a try. I just said, well, let's assume x is a linear combination. X is a linear combination. And then you rewrite into the component form. So basically, we are having three-dimensional vectors. It's going to give three equations like I typed over here. And then, well, let's take a look at those three equations. I think the first equation basically says C1 has to be 1/3. And then C2 has to be 0. And then, indeed, if you put those two values back to the equation in the middle, they won't match. So really, we just figured out here, in this case, x, we cannot find out any solution, C1, C2, such that x is C1u plus C2v. So I'm saying x is really not a linear combination of u and v. X is not a linear combination of u and v. So specifically, the span of u, v, x, okay, it has to be the linear combination of those three factors. Linear combination of those three factors. And clearly, I'm saying this span is different from the previous one. Then how do we know it is really different? So the next part, just to identify how the span would look like, because I know the span, it is a three-dimensional vector. So I'm saying for any vector in the span, and basically, it can be written as the linear combination of u, v, x, right? And also consider this is really not an arbitrary vector in the span. It could have been an arbitrary vector in the three-dimensional space. And then, if, well, as I'm saying, it might be very helpful. Indeed, I think I do have this in the typing part here. Okay, you really want to write this, convert this vector equation into the system of equations. And they also use the matrix multiplication. The coefficient, okay, the coefficient matrix, it is always formed by u, v, x in the column form, column u, column v, column x. Then C1, C2, C3 for any vector. Okay, for any vector. And indeed, for any vector, any vector in the three-dimensional space, in the R3, we always can find out a unique solution, because I suppose you know this matrix here, 3 by 3 matrix, it is invertible. Do you know why it is invertible? There are several things you can consider to find out the inverse of a matrix. Or the same, maybe the easiest one for 3 by 3, you may want to check with the determinant. Because when the determinant is not 0, then we know the matrix is invertible. And when the matrix is invertible, that means we always can find out a unique solution for C1, C2, C3 using the inverse multiplied to the left of the right-hand side. So really it means for any factor in the 3-dimensional space, for any factor in the 3-dimensional, I really should say in this way, for any factor in the 3-dimensional space, it is a linear combination of UVW, and so really it means the span of UV, this should be X, this should be X, okay, this should be X. Any factor in the 3-dimensional space, we always can find out that vector in the span of UVX. So indeed, I'm saying the conclusion here is the span of UVX, indeed, it is the entire 3-dimensional vector space. The span of UVX, it is the entire 3-dimensional space. Thank you for watching.